So thank you all for coming to the Gong Show, which is our chance to be exposed to a lot of new ideas in a relatively short time. I'd like to thank all the speakers for preparing the excellent talks we're going to hear. It's a very impressive lineup. And I also wish to express the hope that at some future occasion, we'll have the chance to invite all of you and many of you in the audience back for a more leisurely presentation than will be possible today. So you'll each have 6 minutes, but there will be a 1-minute warning, which is supposed to happen when my little cell phone here beeps, but I'll draw it to your attention. After 6 minutes, I'm afraid you'll have to end. There will be 1 minute changeover between speakers. During that 1 minute, you can take a quick question from the audience. If somebody thinks of a quick question that can have a quick answer. So once again, thanks to all of you here, both the speakers and the listeners, who are all equally important. And our first speaker will be Louise Anderson of Chalmers University of Technology, telling us about phase transitions in mass-deformed ABJM. Thank you. This microphone?
Well, is this on? Yes. First of all, thank you so much for the introduction. And second of all, thank you so much to all of the organizers for giving me the opportunity to speak here today. I will be talking about phase transitions in mass-deformed ABJM theory. And this talk is based on a paper together with Kostia Sarembo that appeared on the archive this Monday. Now I only have 6 minutes to tell you about it, so there's really no way I'll be able to go into all of the glory details. So my aim for today is to simply give you a vague overview of what we've done and why we've done it. And if anybody has questions or is interested in more details, I'd be more than happy to after the talk. So why did we do this at all? Well, the deep motivation behind it is really to test the gauge gravity duality, where we have the gauge theory on one side and the gravity holographic dual on the other. So if we find exact quantities in the gauge theory that can be computed for all values of the coupling, these can be compared to exact results in the gravity side. In the case of ABJM, the holographic dual is type 2A string theory, and exact results has been obtained for all values of the coupling, such as the free energy and expectation values of Wilson loops, and they've been compared to results from supergravity calculations. But how do we find these exact quantities? Well, we use the principle of localization, where we put the gauge theory on a sphere, which means that the path integral localizes to a matrix integral. And this is sometimes exactly solvable for all values of the coupling, at least in the multicolor limit. So in the case of ABJM, once more, the partition function localizes when we put the ABJM theory on a 3-sphere. And in the large n limit, the saddle point approximation of this integral becomes exact. So the problem reduces to actually solving a set of saddle points equations, and these are solvable for all values of the coupling after some tricks with analytic continuation. But so far I've only talked about the massless theory, and our work is about the massive case. So what do we do when we mass deform the theory? Well, it's like adding a scale. And this scale can be thought of as the radius of this sphere that we put the gauge theory on. So again, we have mass-deformed ABJM theory with this scale, this mass scale of the radius of the sphere. And we have some holographic dual here, which we don't really know what it is, but it's not really a big deal to us at the moment. And we start looking for exact quantities. Now in this paper, we considered 2 versions of analytically continued ABJM theory, following the solution techniques used in the massless case. So we put these analytically continued versions of ABJM theory on a 3-sphere. Once again, the partition function localizes to a matrix integral. We take the large n limit. We end up with some saddle points equations. But unfortunately, these are not solvable for general values of the radius of the sphere. Fortunately, what we're really interested in is seeing if this theory exhibits some phase transitions. And any phase transitions will occur in this region here for infinitely large r. And when the radius of this sphere grows, the saddle point equations simplify and they become exactly solvable. And what we find is this. An infinite set of third-order phase transitions at finite values of the coupling, and they occur at these values of the coupling, which is given by a very simple expression where n is just an integer denoting like the number of the phase. And these phase transitions, they accumulate here at strong coupling. Now in the paper, we used our analytic results and compared them to numerical calculations. And these are just examples for two different phases where the purple dots are numerical results and the yellow lines are analytic results. And they agree very well. The difference is you see the smoothness of the numerical results has to do with the fact that you can't really use an infinitely large r radius in Mathematica. But it becomes better as the radius grows. So let me just finish off with some open problems. Like I told you, we consider two versions of analytically continued ABGM. Now, it would be very nice to analytically continue this back to the original ABGM theory. Unfortunately, this is much harder in the massive case than in the massless one. So that would be very interesting. And also, these phase transitions have been found in other massive gauge theories as well. For example, in Chern-Simons theory and in four-dimensional n equal to 2 star. And in n equal to 2 star, we also have this accumulation of them at strong coupling. And it would be very interesting to know what that corresponds to on the string theory side. So thank you.
Thanks for the beautiful talk. I actually have one small question myself. This is all in the large n limit?
Yes.
Okay, thank you. Our second speaker will be Arash Arnahali, speaking, as you can see, about the chiral anomaly from the superconformal index.
Thank you. Good afternoon. I'm going to tell you about an interesting relation between anomalies and the superconformal index in four-dimensional CFTs. Now, the superconformal index is a Witten index trace -f to the fermion number, refined with these fugacities, tau and y, for charges that basically don't mess with the fermion number. Now, I'll focus on the single trace index at large number of colors, because that's the simple version that is tractable. The other ones are somewhat nasty. Like any other Witten index, this is protected against quantum corrections and can be obtained at strong coupling, so it's frequently used to test supersymmetric strong-weak dualities. Now you can think what other protected quantities are out there that may be related to the index. And CNA central charges are two such protected quantities related to the Weil anomaly of the CFT on a deformed background. There are simple weak coupling trace formulas for CNA, but let's assume we only have a strong coupling description in which there are infinite towers of mesonic states over which these traces would vanish. If we could relate CNA to the index, the fugacities in the index would provide natural and simple regulators for those divergences. At an intuitive level, you may suspect a relation between the index and the acentral charge, because the index receives contributions from the holomorphic spectrum. And the spectrum, you may think, knows about the number of degrees of freedom, and so does the acentral charge. But we haven't been able to find such a relation yet. What we have managed to find is a relation between C minus A and the index, and in a sense, this is even more interesting because C minus A in traditional holographic setting is an order one loop effects in the bulk. Now C minus A partially determines the Weil anomaly and fully determines the chiral anomaly on a deformed background, hence the title of my talk, Chiral Anomaly from the Index. Here's our formula. You simply act with this differential operator on the single trace index at large n, and you remove these tau and y regulators by taking them to 1. The tau fugacity heroically tames the divergence, and as the finite piece you obtain the C minus A that you can compare with the weak coupling trace formulas. Now, this is obtained from a one-loop holographic Weil anomaly computation, but since the formula relates only field theory objects, we expect it to be true independent of holography. And as an application of this, we've been able to prove ADS-CFT matching of C minus A for arbitrary toric quiver theories with smooth Sasaki-Einstein dual. And that provides an infinite number of one-loop tests of ADS-CFT for smooth manifolds dual to toric quivers. Now, so far so good, but you may say you like C and A central charges better because they're of extreme dynamical interest, as the A theorem shows, and extreme quantum mechanical interest, as the entanglement entropy results show. For that, I hope I can report progress in the near future. Thanks for your attention.
We actually do have slightly more time for questions.
Is there any physical meaning for the first coefficient B in front of the divergence? You said the finite piece is C minus A.
That's right. We have been able to compare it with geometrical quantities on the dual gravity side, but it would be very interesting to find the meaning on the field theory side. We don't know.
Okay, thank you very much. So our next speaker will be Sudasatwa Rama from Penn State, talking about effective formulation for quantum systems.
Hi, thank you to the organizers for having me here. So I'm Shudo, and I'll be giving a very brief overview of some work that I've been doing with my advisor, Martin Bojewald, on effective formulations of quantum systems. So all of us already know that why we need effective theory at all. If the full quantum theory is too difficult to construct due to technical and maybe conceptual difficulties, we still want to get some semi-classical behavior in certain regimes where these theories are applicable. But we already have standard techniques to calculate effective actions. Why do we need new ones? And what we are aiming for, what we have in mind, is to get some background independent effective descriptions. So once the background space-time itself is quantized, the canonical formulation of gravity is more complicated than standard gauge theories, and standard particle physics techniques sometimes don't work. For example, it might be because we want to have a non-standard vacuum state, or we might have to accommodate a more general version of general covariance. So that's why we want to focus on in a canonical setting, effective equations. So some very few technical details. We define some moments as expectation values like so, where I've just chosen one canonical pair for simplicity, while here stands for total symmetric ordering. And then we have an infinite dimensional space given by infinite number of these moments and the expectation values of Q and P. And we can have a Poisson structure on this through the commutator of the operators and invoking Leibniz rule. And then we will get an effective Hamiltonian, which will give us this canonical effective equations, which will be basically quantum corrected classical equations of motion. So elaborating on that last point and abbreviating over here, like for brevity, we have an effective quantum Hamiltonian as a function of expectation values of Q, P, and these moments. And then these generates these equations of motion. So if we step back and see what we have achieved so far, instead of solving Schrodinger's partial differential equation, we have an infinite set of infinitely coupled ordinary differential equations. Infinite because there are an infinite number of these moments, and they're coupled because these moments back react on the equations of motion for Q's and P's. They have also got to satisfy the uncertain relations, which are too technical to get into for the purposes of this talk. So the take-home point is, if I have some classical phase-space function and I have a quantum operator corresponding to it, then I want to compare the expectation value of this operator with respect to some arbitrary state with the function of the expectation value of Q's and P's. And effective equations are a systematic way to derive the difference between these two quantities, and these give you the quantum corrected classical equations of motion. So very briefly, a few applications that we have been looking at and that we have looked at already. So it's very easy to derive Coleman-Weinberg type effective potentials. Our motivation here was to apply it to a certain model due to Meissner and Nicolai of two massless Higgs, where particles get massed by a conformal anomaly as opposed to spontaneous symmetry breaking. And we just want to apply these methods there because in certain regimes they are again much simpler than usual techniques. And we also applied this to certain toy models of isotropic and homogeneous cosmology, quantum cosmology, where together with an adiabatic approximation, this helps us derive higher derivative corrections that we expect as terms coming from low energy effective action. And then something that we are working on right now is if we have a particle in a magnetic field in presence of monopoles, then we have a non-associative algebra. And again, standard methods are difficult to implement for such non-associative algebras to quantize such algebras. And we again can get correlation functions coming from these effective equations, even in that case. And this kind of things, similar structures come up in non-geometric closed strings in relation to T-duality and double field theory, as has been shown by this gentleman over here. And finally, our main goal, of course, is to apply all this to find an effective theory for gravity. So in canonical gravity, like ADM, we have a 3+1 splitting, where where the constraints have to satisfy this hypersurface deformation algebra if we have to get back general covariance. And this has some Lie algebraic structure, which is slightly different, more technical than the Lie algebra structure, which has structure functions instead of structure constants. But the main point is once these constraint operators are quantized, they lead to quantum corrections depending on whichever theory you would choose. And we still have to ensure that we have no anomalies, and we still have still got a first-class system to ensure some general form of general covariance. And again, a similar procedure of effective constraints is easier to implement in such situations rather than to implement the whole Dirac program to quantize such theories. Okay, so in conclusion, I guess I'll just leave it up there for you to read. I've already said enough. Thank you.
Thank you. Thanks for the very nice talk, and I invite any brief questions.
Sorry, come again?
Is the function related to the Wigner function?
It can be related in, at least for scalar QFTs, we can relate it, we can have a very mathematical derivation such that it's related to that. But I don't know how it applies to more general systems. We haven't tried.
Thank you. Thanks again. Thank you. Okay, we'll move on to hear from Anandya Day on n=4 mirror symmetry and gauging linear quivers.
All right, thanks everyone for coming. So I'll be touching on things that I did with these gentlemen based in different places last couple of years. Sorry. So the basic motivation of this project was to use, the new muscle that we have due to localization techniques in computing supersymmetric observables, and to use it to learn more about dualities in 3D. So first of all, of course, to discover new theories that are dual, and also to, if possible, uncover new organizing principles of 3D dualities. And then, of course, there is this more grand question of whether 3D dualities, 4D dualities, and 2D dualities have actually something to do with each other. Okay. So because of these localization techniques, we have a lot of control over methods of answering these questions. So let me briefly mention what exactly I'm talking about. So I'm talking about three-dimensional theories with n=4 supersymmetry, 8 real supercharges. And mirror symmetry in such theories is a strictly IR duality. It exchanges the Coulomb and the Higgs branches of the moduli spaces of the two theories. And it naturally means that it exchanges hypermultiplet masses and Fi parameters, which are blow-up parameters of matrix on the moduli spaces. And the corresponding linear map is known as the mirror map, which is one of the most fundamental information that you might want to ask when someone gives you a pair of mirror theories. Now, a crucial role in our story is played by the so-called linear quivers, which are chains of, so these circles indicate n equals to 4 vector multiplets in the UN gauge group, and the boxes indicate flavor group, SUM1 flavor group, and so on and so forth, which is often written in this form. Now, the mirror symmetry in linear quivers directly follows from S duality in NS5, D5, D3 systems. On the other hand, if we are considering mirror symmetry in nonlinear quivers, suppose I had branches here, then they depend on S duality of more exotic half BPS boundary conditions, like orientifold, orbifolds, and that kind of stuff. So the basic point of our work was to show that a large class of, that mirror symmetry for a large class of nonlinear quivers are related in a very interesting way to mirror symmetry in linear quivers. That's the basic idea. So let's consider a simple quiver of this form, 1, 0, 2, 2, 1, 0, and that is known to be dual to 2, 4. Okay? Now let's gauge this U2 flavor symmetry. Let's gauge a U1 subgroup of this U2 flavor symmetry. And we describe how to do that using S3 partition function in our paper. But once you do that, there is an interesting result on the other side of the duality. So what happens is that gauging on one side of the duality basically results in ungauging on the other side of the duality. So you had a U2 gauge group sitting here, and that reduces to an SP1. So this is the most elementary example of gauging that we have. Now, this is, of course, generalizable to a very large class of quivers with unitary and symplectic gauge groups, and for non-abelian subgroups of flavor symmetries. This was an abelian example. And here are some examples. So this is like a star-shaped quiver with some tails. Here are a bunch of affine D-type quivers and their mirrors. So in each of these cases, you can start from 2 or other, actually it's an infinite family, but 2 linear mirror pairs, and then gauge, and you can read off what the dual theory is on the other side using S3 partition function. So here are some more examples, some E-type theories and so on. Now there is a very interesting byproduct of this analysis. So it's been known for a while that for certain affine quiver theories, the naive S duality gives bad mirrors. Okay, so this is one example. This has been treated by Hanani and Zaffaroni long back. You can see that this SP node is a bad node. Okay, so the question is whether we can come up with good mirrors whenever such bad mirrors actually exist. Now it turns out that this gauging procedure actually gives you a way to construct such stuff. So the answer is this is a good mirror. And you can obtain it in the following fashion. You start with these 2 theories, linear, and you gauge this U2 as a U1 cross U1. You get a affine D quiver with appropriate hypermultiplets, and this is the result that you get. So this gives you a very nice way to construct good mirrors where there are none. And there are 2 more examples that you can do this to, and expect to get. So future directions. So extend this story for generic orthosymplectic quivers. That's something that we have not done. And if we can do that, then this might be a tool for generating good mirrors whenever naive S duality gives a bad theory, with a large number of cases with orthosymplectic quivers. Then to understand the n equals to 2 version of the scheme, that's the next step. The 6D interpretation is in terms of the DGG. So what basically this gauging means in terms of triangulation of 3 manifolds is also an important thing that we need to understand. And then finally, there is a case of non-Lagrangian mirrors, which I don't have time to explain. Thank you very much.
Thanks. Can you just clarify the criterion of what's a good mirror?
Well, there are 2 ways.
Yes.
One is the Guyot-Witten criterion.
I wasn't certain if that's what you meant.
The
Yes.
other thing is that you can construct the S3 partition function and see if it blows up. So in all these cases,
Yes.
whenever there's a bad, just write down the S3 partition function as a function of masses and FI parameters, you'll see that whenever you have a Bethe theory, there's a blow up in the partition function.
And are the, so do the, is it actually one-to-one? I mean,
In what sense?
if a mirror is good by the R symmetry criterion, do you also find that the
Yes.
partition functions
Yes.
work?
So far, all the examples that I have encountered.
Thank you. Any other very quick questions? Okay, thank you, and then we'll move on to the next talk. Thanks, the speaker. I was looking to see the next speaker. So we'll be hearing from Olaf Englund on the Twistor String Theory We.
Yeah, okay, so I'm going to talk about a twistor string for the APJM theory. It's based on this paper with my advisor, Riemann. Basically, the idea is, 10 years ago, somebody created a twistor string theory for integral to 4 super Yang-Mills, and now we want to do the same thing for APJM, okay? So, first of all, just remind you if you know it, and then otherwise tell you if you don't know it. So, in 4D, you define spinors this way, and then you create some twistors and conjugate twistors. While in 3D, the twistors look like this. So 4D, there are 2 spinners with two component spinners. 3D, there's only one 2 component spinners, and then there's some Grassmann variables. So so there are fewer degrees of freedom in the 3D twistor space. Okay. So in integral to 4 super Yang-Mills, all tree-level amplitudes can be incorporated into this formula, where n is the number of external particles. If you don't understand what this means, k is basically a number that tells you something about the helicity. And yeah, those are the integration variables, and those are some functions of the integration variables. And this makes the integral meaningful. Now this can be found more or less directly from a string theory in twistor space. So B model constructed by Witten, open string by Berkovich. So I think it was 2 years ago, APJM was shown to have, their amplitudes could be put into this formula, which looks very similar. Like there's some additional functions here, but other than that, it looks sort of similar. So you might ask, so can this be the result of a twistor string theory? And that's basically what we're doing, what we're constructing. So, yeah. So the funny thing is, I doubt if you're going to follow this, but so we basically do something that looks a lot like Berkovich. The strange thing is, we're actually using a larger space. You might think, oh, because the twistors in 3D have less degrees of freedom, but we can use some smaller space, but actually we need to enlarge it. Because if you use something that's too small, we're not going to get the conservation loss we need. Like, we're not going to get momentum conservation. So that's pretty bad. So we actually need some bigger, even though it's just 3D. And then So if we just followed sort of what Berkovich was doing, we would have vertex operators that look like this, there's some current algebra, and there's some worldsheet instantons that basically, so these are some external data, and these are the worldsheet fields which are given in terms of some collective coordinates that are integrated over. So this would be more or less how you do it if you just followed Berkovich's thing. But now we have introduced these extra dimensions that we don't want, so we're going to get rid of them. So first of all, we're going to break symmetry, and we're going to get rid of the 5th dimension, just so we're going to open up to treating this completely different from the other fields. So that leaves us with something that looks like a 4-dimensional theory. It's basically an integral to 4 super Yang-Mills with some extra shit attached to it. And then we need to use these projectors. And these projectors, what they basically do is they set some conserved quantities to 0, and you can already imagine that can be problematic, because if you set a conserved quantity to 0 everywhere, then naturally the sum is going to be 0, and you're going to get a delta function of 0. So this is something you need to be careful how you do it. And then we have to do some tricks to actually, because we don't want all of these states, but I'm not going to go into what it is. But we can somehow, at least at trivial level, truncate to only 2 of the vertex operators. And then how you're actually going to deal with when you do these projections. The problem with the projection is they introduce shift symmetries. So you end up with an integral where you're integrating over an infinite set of basically equivalent states. So you need to somehow remove this shift symmetry, and this shift symmetry, they can be exchanged. They can be exchanged for this factor that does not depend on the integral variable. So we just pull it out of the integral and just drop it. Well, if you notice, this is basically some zeros. But you can pull it outside, and then the remainder is in fact the ABJ amplitude. So this is basically what we've been doing. So the tree-level amplitude for ABGM can be collected into a formula that's reminiscent of one for n equals 4 Young-Mills. The formula can be derived from a string theory in Twistor space, but it requires a larger theory with external data then being projected down to some super Twistor space for ABGM. And the construction actually allows a certain modification. So there's some interesting questions, like does the full theory even mean anything? And does the modification have any meaning other than, that are they just weird artifacts of our constructions? Okay, so that's it.
Any brief questions? Yeah, yes? Can't quite hear. Speak up.
I couldn't.
What were the y and z variables?
There were several y and z variables. The capital Y and Z
capital
variables,
ones.
they were basically the space that the strings were moving in. Okay? Maybe that was what you were quite. So basically you have a space where that is sort of like a Twistor space. So the strings move in something that you could classify as some kind of Twistor space, in a way. Okay? Ask me afterwards, otherwise.
I think you stated this already, but can you remind us in just one sentence how the space you work in is related to the mini Twistor space you had near the beginning of the talk?
Well, basically, we have to project down, so it's basically something that's really big, and then we just project down the external data. So it's like mini Twistor space, but just with some extra dimensions added in there because we need them.
And then you have constraints or gauge invariances or something that reduce to mini Twistor space?
What?
Well, maybe I should get you a fuller answer later.
Okay, yeah.
Okay, so the next speaker on topic are Victor Gorbenko on the QCD flux tube from approximate integrability.
So I'm going to tell you how to calculate the spectrum of flux tube in the pure Young-Mills theory using integrability. So for me, flux tube is just a string-like object which breaks space-time Lorentz invariance. So it consists of d-2 Goldstone boson of this broken symmetry, and it's just an effective field theory with the cutoff set by the string length, which in QCD is of course of order of lambda QCD. So the action is constrained by this nonlinear symmetry, and you see the first term is just the usual Nambu-Goto action, but of course there are corrections with higher derivatives. Luckily for us, at the one loop level, the only term which is not a total derivative is the extrinsic curvature squared, but it vanishes on shell. So there are no one loop coupling constants in this theory, which makes the prediction of our effective theory more universal. So we can expand this square root action, and you get some quartic couplings. All the coefficients are fixed by nonlinear symmetry, and you can just calculate perturbatively the spectrum. So we'll be compactifying this action on a circle, calculating the spectrum perturbatively in the length of the circle, in the length over R, where R is the length of a circle. So from the bulk theory point of view, it will mean the spectrum of a flux tube winding once around the compact direction. So let's see what it gives. So on this plot, you can see the dots are the lattice data, and the solid lines are the results of this perturbative calculation. And as you see, when the strings get short, the calculation, the perturbative calculation diverges. On the other hand, these dashed lines are the results of the quantization in the light cone gauge, this famous square root formula. However, this formula cannot be correct because the light cone gauge does not respect Lorentz invariance away from 26 dimension. So when we calculate two particle states, so two particle means there are just two goldstones living on the string, the situation gets even more dramatic because the perturbative calculation diverges basically everywhere where we have data. However, the wrong formula fits the results pretty well. So that was the confusing situation, that the wrong formula fits much better than the perturbative calculation. So this suggests that we need some smarter way to calculate the spectrum. And to figure out this way, let's notice that the spectrum is actually not just the function of the radius, but also the function of the momentum of the states, of the goldstones that's comprising the state. So it suggests the procedure to calculate the energy in two steps. First, we go to the infinitely long string and calculate the S matrix of goldstones scattering on this string. And then we will try to get the spectrum from this infinite volume S matrix. So first step is pretty straightforward. The second step can be subtle in general. Luckily for integrable theories, there is a procedure called Thermodynamic Bethe Ansatz, which gives you exactly the spectrum of the theory if you know its S matrix. We know that this QCD string in 4 dimensions cannot be an integrable theory. However, it is very close to an integrable theory, and non-integrability only shows at the one loop 6-point function, which is a 4 ls to the 6. So what we're going to do next, we're going to use the S matrix to the level where it's integrable and plug it into the Thermodynamic Bethe Ansatz. So I don't have time to explain you what Thermodynamic Bethe Ansatz is, but I put all these formulas on the slide to compensate for the plots that I have, so my talk doesn't look too experimental. And so you see, this is basically the machine where you plug in the S matrix. The S matrix enters through the phase shift, which is a logarithm of an S matrix, and it gives you the spectrum, which depends on the radius. For example, if you plug in the square root formula for the light cone string, you get a very nice S matrix, which is just exponent of the Mandelstam variable. This S is the product of the momenta times the identity in the flavor space. So we do this for our one loop phase shift, and what do we get for the ground state and one particle state is basically the light cone formula. So this explains why the wrong light cone formula fits the data so nicely. So let's see what happens for the two particle states. For the two particle states, now the solid lines are the results of TBA with this one loop phase shift. So you see that it matches the data much better than perturbative expansion. Moreover, it does not diverge in the region where we have data. However, still so the different colors suggest different quantum numbers with respect to unbroken SO2. We see that the pseudoscalar state is pretty far away from our predictions. However, the expansion is convergent. So it means that we need to add some new ingredient to our theory. And from the shape of this state that does not depend much on the radius, you can guess that we need to add a massive particle. So once we do this, we add the massive particle on the world sheet of the string, we couple it, it contributes as a resonance in the pseudoscalar phase shift as the usual arctangent. We have two new parameters, which is the mass of the particle and the coupling, and we plug it into our TBA equations, and that's the solid lines you see. This is the final feed that we get. So it got improved by an infinite amount of sigmas compared to the initial perturbative expansion. And what we can conclude is that by means of these non-perturbative techniques, we discovered a first massive excitation on the world sheet of the QCD flux tube. And what is surprising, it's not the breathing mode of the string that one would expect. That would be a scalar particle. It is a pseudoscalar particle. Thank you for your attention.
So any very brief questions about this? In that case, let's thank our speaker again. So now we'll hear from Shahid Haq about attractive C functions from holography.
Thank you. I would like to thank the organizers for giving me this opportunity. I'll talk about attractive C functions from holography. This is basically work in progress with Arpan Bhattacharya, Vishnu Sala, Alvaro Soria, and Suresh Nampuri. So basically, we have a proposal for a C function from holography by using the attractor mechanism for certain black hole and black bin solutions. Now I want to quickly go over the C function. Now in quantum field theory, an important problem is how to define a measure for the number of degrees of freedom that decreases along the RG flow and has stationary values at the RG fixed points. Now RG flows can be seen as a one parameter motion in the space of renormalized coupling constants with beta as the velocities. Chomolachikov showed that for a unitary renormalizable QFT in 2 dimensions, there exists a positive definite real function of the coupling constant, which has some nice properties, like it's monotonically decreasing along the flow. It has it's stationary at the RG fixed point, and it coincides with the central charge at the fixed points. Now, very quick review about the attractor mechanism of the black hole. Now, black hole solutions can appear when a superstring theory is compactified to lower dimensions. Now, these compactified theories usually have moduli dependence, and they can appear at the black hole solutions, which can exist for genetic values of the solution, genetic values of the moduli at infinity. Now, so there's a danger that the entropy of the black hole might depend on the moduli. Now, for the black hole, the entropy depends on the behavior of the solution near the horizon, not the infinity. So a resolution would be the moduli depends on the radius in such a way that near the horizon it's completely determined by the charges. So in other words, for the moduli, the radial dependence is determined by some differential equations whose solutions flow to determine the values at the horizon, not at infinity. So we'll use this attractor mechanism to propose our C function. Now this is sort of the outline of the proposal. So we looked at some dynamically charged black hole and black bin solutions. Those are the extremal black bin solutions, and those are solutions from n equals 2 gauge supergravity. Now the important point is they have ADS space asymptotically, and also some ADS factor at the near horizon with a different dimensionality. So we're talking about, we're looking at the RG flow between 2 different dimensional CFTs. So let's say you have a ADS D plus 1, and then it flows down to, the attractor flows to a D prime plus 1. Then the CFT flow is CFT D to CFT D prime. Now, we are looking for, from the attractor mechanism, we're looking for an affine parameter that can have the nice properties of the C function. So this is the details about the proposal. So if you consider a metric, like a Black-Bone metric, and from the null energy condition, you can write down this relation. And for b greater than 0, we can have this condition b double prime less or equals 0. Now we want to construct a function that has the derivative greater or equals 0. So this is our proposal. The A function goes as this, where this lambda and kappa square are constants. So then, of course, it satisfies this condition that we want. Now it's a monotonically decreasing from EV to IR, and also for the CFT on the ADS background, this proposal is constant. Now for BPS for a 4D attractor flow equation, so there are some 4D attractor flow equation where this war factor, the derivative of the war factor actually depends on this function, this Kali Z, which is essentially the net central charge in the theory. So we can rewrite the proposal in this fashion. Now we can extend this argument for 5-dimensional solution as well. Now we have 2 arbitrary constants in this proposal, so it would be interesting to fix them. Now there are nice Black-Bone solutions, Black-Bone solutions, which are in these references. Now one of them would be the solution where the asymptotic is at ADS 5 like, and the near horizon geometry is ADS 3 times R2. Now the asymptotically, then it's dual to a CFT4, The 4D, in 4D, there are two central charges, C and A, C is not monotonically decreasing, so we can rule out that. So we know the fixed the central charge at the 4D theory, and for the 2D CFT, we have one central charge, so we can fix the other end, so we can fix the two constants, and then know all about the F function. I guess that's all I want to say.
Any very brief questions? So, when you said independent of supersymmetry, I guess you meant it didn't matter exactly how much supersymmetry there was for the attractor mechanism.
It can be done independent of the supersymmetry because there is some attractor mechanism for non-supersymmetric solutions.
Oh, okay. Thank you.
Sure.
One, two, three.
Do we have the next slides?
Yeah.
Okay. So now we'll hear from Fedor Levkovich-Masliuk on quantum spectral curves in n=4 at small spin.
Thank you very much. Let me thank the organizers for giving me this great opportunity to speak here. So my talk will be based on this joint paper with Nikolai Gromov, Grigory Sizov, and Saulius Valatka, where we obtained a new exact result in n=4 supersymmetric Young-Mills theory. So we are considering this theory in 4 dimensions, and it is known that it is due to superstrings on ADS5S5. We will consider the limit of large number of colors, the T-Hooft limit, when the T-Hooft coupling is fixed. And in this limit, a very remarkable feature arises. The theory, an integrable structure appears. And this gives hope to solve both theories exactly using methods based on integrability. In particular, the operator conformal dimensions have a very simple description. So recently it was understood in this paper that they can be computed by solving a Riemann-Hilbert problem. This formulation is based on the Thermodynamic Bethe Ansatz approach, and the result is called the P-mu system or the quantum spectral curve equations. So this is a set of nonlinear equations for 10 unknown functions, P and mu. They have branch points whose location is related to the T-Hooft coupling. The equations express analytic continuation around these branch points in terms of the original functions themselves. This is a closed system of equations, and it determines the spectrum of single trace operator conformal dimensions exactly at any value of the coupling constant. Also, in the classical limit, these equations encode the classical spectral curve of the model. In our paper, we applied this formulation to study operators of this form, which consist of scalar fields and covariant derivatives D. And it is interesting to treat the number of covariant derivatives S, which is called the spin of the operator, to treat it as a continuous parameter. And we will consider the rather peculiar limit when this number approaches 0. So in this case, the anomalous dimension can be expanded like that, and the expansion coefficients are non-trivial functions of the coupling. We were able to compute them exactly, the first two of them, exactly at any value of lambda from the P-mu system that I have just discussed. So the first coefficient was known before, and it is written in terms of Bessel functions. We reproduced this result from the P-mu system. Our main result is the second coefficient, which we also managed to compute exactly at any value of the coupling. It has the form of a double integral of some function, which is straightforward to expand at weak coupling, and there it matches the prediction coming from gauge theory, while at strong coupling it matches the predictions coming from string theory. So we can see an interpolation between gauge and string theory as we increase the coupling constant. There are several applications of our results. We were able to compute several new terms in the strong coupling expansion of the BFKL intercept. And another application is that we can access the strong coupling expansion of operators with fixed spin by performing a re-expansion of our result. So using our data, we are able to predict a new coefficient in the strong coupling expansion for an operator of this form. This is the so-called Caniche operator, which has been very well studied before. So we computed the new coefficient in this expansion, which serves as a very non-trivial prediction for string theory at 3 loops. Now let me summarize my talks. So we applied the quantum spectral curve or PMU system formulation to study anomalous dimensions of operators made of scalar fields and covariant derivatives. In the limit when the spin goes to 0, we have computed the coefficient of the S squared at any value of the coupling constant. The results reproduce known predictions at weak and strong coupling. And let me also mention that a similar approach can be used to compute results at all coupling in several other situations where we have near BPS observables. Thank you very much. So the PMU system itself is derived from thermodynamic Bethe Ansatz equations, which are derived from well-known considerations for integrable theories. So this information is not put in. This is not an ansatz. Well, this is what we get from the PMU system itself. Also, it is consistent with other information concerning these operators. For example, at weak coupling, this is immediately seen. At strong coupling, known results also suggest this.
Thanks very much again. We'll hear from Chen Ma on S duality for D3 brains and S and R backgrounds. I think it's working.
Okay. Oh, no. We worked on this project for D3 brain in NSS RR backgrounds. We only consider flat spacetime and a constant background on the wall filing, and this background we do not have a time component. And we can see S duality by perturbative way to study it. The correlator is a Pei-Ming Ho and well computational thermodynamics. And we already submitted this work on arXiv. Now let me use a reference to show the development of history. The first paper shows the stack of the BLG model to get the number parcel N5 brane. And this number parcel N5 brane only has a constant background on the 3-dimensional space. And then we can use a directional dimension reduction to get the NSS D4 brane on the second paper. Then by double dimension reduction to see R D4 brane, it's the first time to see this R brane low-end theory. And then we can do the generalization from R D4 to R DP brane. It's a DP minus 2 brane ending on DP brane. It's just a Poisson level. And especially for P equals 3, we can see S duality. And let me say the convention of our convention. We have 2 types of space-time. The first type of space-time is one direction with our background. We call it S alpha, no dark space. And then we use S mu dark space to denote direction with the background. So this diagram is our approach to get the RD3 brane. If we have a well-defined N5 brane theory, we can use a direct double dimension reduction to get the R-default plane in three-form background. Then we perform the direct dimension reduction to get the RD3. Then we can switch the ordering commodification to get the NSS D3 plane. And then we say that they are the same theory, then we call it the D3 plane. So we want to say that the ordering of commodification does not affect the physics. So we should say, in other words, we can say NSS D3 plane is related to RR D3 plane just by theory definitions. So it's a non-perturbative way to understand. Maybe I need to say we can use perturbative way to all orders to understand S duality. Okay, at first we show a concrete example for Poisson limit. If we consider NSS D3 plane to all orders, it's just a Moyal gauge theory by Moyal product space. But now we show a Poisson limit. That is just a Poisson bracket. Then RD3 plane can be obtained from the Mabu Poisson N5 plane just by reduction, dimension reduction. It's a misdescription of two-form B field and the one-form gauge potential. If we integrate out the two-form B field, then we get the Yang-Mills term at the leading order. Then we can show they have S duality. It's a definition of field strength. They are covariance. They have a covariance, and the B header is satisfied by this complicated relation. So B header is a function of a one-form gauge potential and a two-form B field. Now let me say how a double scan limiter. It is a double scan limiter of NSS and RR. And this double scaling limiter can ensure that our effective warp-following theory decoupled from the bulk. So even this NSS side company is weaker and here is strong. We should say this effective warp-following theory still be good effective theory. And if we use S duality on a scaling limit, double scaling limit, then we get this scaling limiter. So it's still consistent. Now we introduce how to perform S duality to all orders. NS is just a familiar Moyal gauge theory. It's a Moyal product. G is just an inverse background. So we do a perturbation to the large background. And from the Poisson limit, we can have these three relations. Then we congratulate these three relations are failed to all orders. Then, from the previous three relations, we can see these four field strength relations. And we can also see this new product space, new product, double star product. It's a new double star product. And this new double star product comes from the Hongyu's paper first time. And we also see these three field strengths are covariance. And the next one, we do not see covariance now. But however, if we add possibly, okay, this is just possible. If we can put a suitable total dividend, we can see covariance maybe. Okay. However, this double star particle does not have associative relation. But if we can perform integration, it's associative. So the gauge inference on this theory is easy to see. And then we also have a non-trivial relation between double star product and the double star and the star product. So S duality may just exchanges two products. Now I show conclusion and the virtue. We already extend S duality to infinity, and the first time we see non-commutative RD3 plane beyond Poisson. And it also shares the light on the EN duality of non-abelian gauge theory because of non-commutative gauge theory is similar to the non-abelian gauge theory. So we say that abelian and S duality can tell us what is the new structure of a field theory. And the main point is that non-abelian gauge theory is related to field. So our S duality also related to the field. So the situation is similar. And the final question: how to find Noto?
All right, hello, I'm Travis. I'm going to tell you about a paper I wrote with Sav Sethi called Domain Walls, Triples, and Acceleration. In the paper, we introduced a construction for a domain wall in the E8 heterotic string theory. The walls interpolate between distinct three torus vacua that are built out of so-called triples, which are gauge configurations I'll tell you about. These walls resemble brane and anti-brane systems, which suggest that there's a possible role for them in finding acceleration in string theory backgrounds. So the main part of the construction of these walls were, as I said, triples, so let me tell you about those. These come about because on a three torus, it turns out that the moduli space of flat connections, that is, flat connections meaning for which the field strength vanishes of gauge groups E8 and others, turns out to be disconnected. The components of this disconnected moduli space are labeled by their Chern-Simons invariant, which in this case happen to be fractional. And we can use these triples, these are the triples, these gauge configurations with fractional Chern-Simons invariants. We can use them to form heterotic string vacua in the following way. We take a triple with a Chern-Simons invariant CS1 embedded in the first E8 factor. Then we take a triple with the opposite Chern-Simons invariant in the second E8 factor. Together, this gives a total Chern-Simons invariant which vanishes, which allows us to set the H flux and the field strength to 0, giving an honest torus vacuum. So now these are the vacua between which our domain walls will be interpolating. But I told you before that these domain walls resemble a brane and an anti-brane. So let me tell you how that comes about. So taking a step back, a single one of these triples can turn into something like a brane. And the reason is that these triples are topologically trivial in the sense that they can be unwound continuously along a non-compact direction, y. And this is a Euclidean Yang-Mills configuration in 4 dimensions, which has a non-zero Pontryagin number. And it turns out from a result by Stern that they can be self-dual or anti-self-dual, or in other words, they're instantons on R cross T3. Now, in the heterotic string, an instanton on R cross T3 resembles an NS5 brane with a transverse R cross T3. And this is what I mean when it's a brane, and then for a self-dual instanton, and then an anti-self-dual instanton would be an anti-brane. But the existence of even these objects is somewhat tricky because the back reaction of gravity in the one non-compact direction is incredibly strong. And it turns out that these objects don't really even exist on their own in pure supergravity, though they may exist in string theory with higher order corrections. Nevertheless, though, we can consider putting 2 of these, a brane and an anti-brane, together in a non-supersymmetric way to form a domain wall. So let me explain that a little further. So this diagram here, on the left and the right, we have the red and the blue represent asymptotic 3 tori in this one non-compact direction y. And on each of these 3 tori, there is one of the vacua that I described, which is composed of a triple and an anti-triple of the opposite Chern-Simons number. Each of these triples can be unwound along the y direction, which then interpolates between one of the heterotic vacua with the triple and anti-triple and another one, or maybe a trivial vacuum. And then since all of this is happening in just the R cross T3, then embedded into supergravity or string theory, there's an extra 5+1 dimensional domain wall on which interesting things can happen. So this description I gave is just, the gauge theory here is a good field theory domain wall, but it's, of course, more difficult to embed this into supergravity and string theory in general because then there's gravitational back reaction and so on. So doing so, though, seems like it's worthwhile to try to do because these domain wall solutions, like I said, may exhibit acceleration. They're non-supersymmetric, and being a brane and an anti-brane sort of object, they likely, or they do attract each other. That's one interesting behavior they can have. Another interesting behavior is the potential for this non-compact direction actually spontaneously compactifying. But there are many open questions in actually performing this embedding into string theory because it's difficult, it's non-supersymmetric, and so on. In addition to that, though, it's possible to even embed this, or there exists a possibility to embed this rather than into a flat Minkowski background, but into a background with an ADS. So, for example, ADS3 cross S3 cross T4 in the heterotic string, or the type 1 string. And it might be possible to embed one of these triples and domain wall type constructions in there and get even a possibly holographic interpretation for for the accelerating domain wall. But there are many, many open questions, and this work is just sort of in its infancy. So I'll end there.
Since the domain wall is built from instantons, why isn't it supersymmetric?
The domain wall is a brane and an anti-brane, so it's like an instanton anti.
For example, could you instead have, so for example, you have in mind instanton of instanton number a third, anti-instanton of number minus a third, but could you instead do 1/3 and 2/3 so they would preserve the same supersymmetry?
I believe no. In that case, you wouldn't be interpolating between an actual heterotic vacuum, so you would.
Oh, you would turn on an H field. I see. I see. You would turn on an H field. Okay. All right. Thank you. Any other quick questions, though? Okay. Then thanks, Travis, again. Okay, so Jun Nyan will tell us about localization of 2D semichiral multiplets.
Okay, thank you very much for the introduction. And I would like to thank the organizer for giving me this opportunity to speak here. And this talk is based on the joint work with my collaborators. Let's start with some definition. 2D n equals 2,2 supersymmetry. There are two supercharges, two without bar and two with bar. And there are four corresponding supercovariant derivatives, and they satisfy these commutative relations. And we can use this supercovariant derivative to define some superfields. There are chiral superfield. They're eliminated by two bar supercovariant derivatives, and there are twistor chiral. These two are well-known superfields. And there are also left semichiral and a right semichiral. They are just, we release some constraint. And these two superfields, they are less well known. So why are they interesting? Why are they worth studying? The reason is following. Let's consider 2D n equals 2,2 gauge linear sigma model. It can flow to some nonlinear sigma model. And there are complex structure of the target space. If we only consider chiral and twistor chiral, then the two complex structure, they always commute. To have non-commuting complex structure, we have to use semichiral. And so my motivation is to study the most general gauge linear sigma model, also as well as the nonlinear sigma model, and to localize the theory with semichiral and use the result to test some dualities. And also because the target space in general, it has torsion, so we are study sort of generalized scalar geometry. This is a seamless model we can construct, use semichiral, which is gauge linear model. And we first we studied this model on flat space. And we found there is no superpotential, and there is no anomaly, neither U1b nor U1a, and there is no generated effective twistor superpotential. And we can show that this model is T-dual to a nonlinear model consisting of chiral and twistor chiral. Next, I want to localize this theory on a sphere and torus. Okay. And some speakers, they have mentioned they use the localization technique. Let me very briefly review the basic idea of localization. Suppose we have a gauge Sousa invariant action, and I add another Sousa invariant and also Sousa exact term to this action, and there is a coupling constant in front of it. Then there is just one line proof that the partition function is independent of this coupling constant. So I can take the limit, this coupling constant goes to infinity. And if this Sousa exact term that I add to the action has a positive definite part, then it will suppress the whole partition function to 0. There is only one possibility which can give the non-zero contribution to the partition function, which is this term itself equals 0. In that sense, we're doing the path integral not over the whole infinite dimensional function space, but just to some special solution. So in that sense, it's localized in some point in the function space. So I just solve this equation, I get some classical solution, then I expand around that classical solution, then just do this, evaluate a Gaussian integral, then I get the classical part plus one loop part. That's the basic idea of localization. So this is general partition function, should look like this. And the classical part is fairly easy to calculate. And I'm going to focus on the one loop determinant part. For the chiral gauge linear model, two groups of others, they calculate the partition function. I want to draw attention to this chiral partition one loop determinant. It's a gamma function divided by another gamma function. Okay, next step, I'm going to localize the theory I mentioned with semichiral on the sphere. And this is our result. And you see that up to an overall constant, which is irrelevant, it's a product of two gamma function divided by gamma function. So just use the one loop determinant of the partition function. We show that the gauge linear model consisting of a chiral, semi-chiral superfield is equal to two chiral with opposite charge. And next, I'm going to localize the theory on the torus. And it's well known that it's another definition of elliptic genus, which is introduced by Professor Witten somehow 30 years ago. And again, this is chiral part of the partition function, and this is our result. It's two product two chiral. Okay, let me summarize. I localize the theory on S2 and on the torus. And next step, I want to check dualities. This is for future research. And maybe we can extract some Gromov-Witten invariants for generalized Kähler geometry. Just similar to these authors, they prove that suppose we have chiral gauge linear model, partition function on the sphere, then we can calculate Gromov-Witten invariants fairly easy. And yeah, that's all what I want to say. Thank you, Mark.
Any very brief questions? Can you tell us a word about the kind of metric you had in your example? About 3 pages ago, you had an example. I think you probably can't go back. Just describe it.
You mean the sphere or the torus?
No, your target space that was dual to one with a chiral and a twisted chiral.
Yes. Oh, that's fairly complicated.
Okay.
Yeah, there is complicated Kähler potential gives the metric and the B field.
Okay. Well, maybe I'll hear more about it later on then.
Okay, thank you.
Okay, thanks again. So, Ankar Parikar will tell us about holographic geometry of the renormalization group and higher spin symmetries.
Thank you for giving me this opportunity. So it's widely believed that holography is some sort of a geometrization of the renormalization group. This idea has been largely explored from the bulk point of view, basically because attacking the problem from the field theory side is hard, because most known examples of holography involve strongly coupled field theories. However, the case is somewhat different for the higher spin vector model duality. In this case, the field theories involved are free, and so one might hope that this sort of provides an accessible testing ground to study more about the connection between holography and RG. So I want to tell you a little bit about the work we did in this direction. It's largely work in progress still. So we started with the theory of free massless fermions, n of them, and the idea was to study the RG flow of this theory under arbitrary ON singlet, single trace bilocal operators. So there are two of them in this case, pi and pi mu. So we added a term to the action which deforms away from the free fixed point by introducing the bilocal source A, which is a pseudoscalar 0 form, and a bilocal 1 form, W mu. Of course, because this is free field theory, it has a large amount of symmetry. In particular, all field redefinitions of this form, which are bilocal maps on the fields, would satisfy an orthogonality condition. You can show that this is a symmetry of the theory, provided you also require the sources to transform like so. In particular, the 0 form, you'll note, transforms tensorially, while W mu transforms like a connection. And we believe that the relevant geometry here is that of the infinite jet bundle, In particular, W mu can be thought of as a connection on the infinite jet bundle, while A is a section of its endomorphism bundle. Okay, so the free fixed point then corresponds to setting A equals 0 and choosing W mu not necessarily 0, but any flat connection. Okay, and then by perturbing away from this background, we could study the RG flow equations. In particular, they take a neat geometric form. The beta functions here are tensorial, and we could compute them using the Wilson-Polchinski exact RG formalism. We could also use some classical physics, in particular Hamilton-Jacobi theory, to show that the RG and Kalin-Zemanzik equations are essentially Hamiltonian equations of radial evolution. We could write down a quote-unquote phase space action, which reproduces all these equations of motion. And by going back and essentially solving these equations perturbatively, we could show that you can reproduce all the correlation functions of the field theory. We encounter, in doing so, we encounter bulk Witten diagrams. I've just demonstrated an example here, but of course, I don't have the time to explain this in any detail. So just to summarize, a simple field theoretic exercise like sourcing operators in the field theory leads us to consider geometry on the infinite jet bundle. The renormalization group extends this geometry into a one high dimensional space, basically the RG mapping space, which we might think of as the bulk. The RG equations that we encounter have some resemblance with those which appear in Vasilyev's higher spin theory, but we haven't been able to make a precise match yet, and that's essentially the next step. That's work in progress. And of course, this analysis can be extended to other vector models, in particular bosonic vector models, non-relativistic models, etc. Thank you very much.
What is the infinite jet bundle?
Okay, so when you have a field theory, you think of the fields as sections of some bundle on the space-time of the field theory. So what you can do is, for all these fields, you can think of equivalence classes of fields which basically agree at a point up to, say, R derivatives. And the equivalence, the vector bundle of all such equivalence, so these equivalence classes are called jets. And if you construct a vector bundle involving all these jet spaces, then that's called the rth jet bundle. Taking R to infinity, you get what is called the infinite jet bundle. Sorry, that was a long answer. But.
Is there another question? Okay, in that case, thanks again for the talk.
Thank you.
What do you will tell us about offshore string theory?
Thanks for this opportunity. I will be talking on offshore string theory, and based on these works I did with Arnab Rutra and Ashok Sen. So I will start by mentioning some issues in perturbative string theory. First one is that Polyakov formulation of string theory compute S matrix elements directly only for external states which do not suffer from mass renormalization. And the underlying reason is that usual formulation demands that vertex operators should have tree-level on-shell momentum. And the second issue is that it does not tell how to do a systematic perturbation expansion around dynamically shifted vacuum. And this is because standard formulation requires that background satisfying classical equations. Then how do we proceed? A direct way is to define off-shell Green's function. There are two ways to define off-shell Green's function. One is string field theory. And other way is just generalize Polyakov prescription without worrying about any string field theory or anything. And we will follow this pragmatic approach, and that's enough for addressing issues which are accessible to string perturbation theory. To define off-shell amplitudes, first you need to give up the conformal invariance of vertex operators and define appropriate local coordinates on the world sheet. But these off-shell amplitudes have a problem. They are not invariant under conformal transformations and depends on the choice of local coordinates on the world sheet, which is a spurious data. Now it's possible to show that these physical quantities that one can define using these off-shell amplitudes, just like S matrix elements and physical masses, they are independent of choice of such local coordinates if we restrict to a class of local coordinates having some special property, which is called gluing compatibility. I will explain what is this gluing compatibility. And The good thing is that local coordinates induced from bosonic string field theory in Siegel gauge has this property. So what is gluing compatibility? You can use plumping fixture to construct higher genus surfaces by gluing lower genus surfaces. Now once you construct such surfaces, this plumping fixture procedure induces some local coordinates on higher genus surfaces. And that local coordinates in the degeneration limit matches with that of the original lower genus surface. And this is the gluing compatibility of local coordinates. And this property is necessary to make sure that offshell amplitudes have factorization properties. Now, you cannot construct all Riemann surfaces by gluing this using plumping fixture. There are a family of Riemann surfaces that cannot be produced by plumping fixture, and we can call them as contributions to one particle irreducible amplitude. And surfaces that can be produced by gluing 1ps are called contributions to one particle reducible amplitude. And if you use this gluing compatible local coordinates, this allows us to divide contributions to offshell amplitude into one particle irreducible and one particle reducible contributions. So you can write down a 1P decomposition of full propagator. Like in quantum field theory, if you restrict to bosonic string theory and NS sector of heterotic and superstring theory, one can show that you can write this as an algebraic expression which you can sum up and then get a compact expression. Here delta is the string propagator and F is the 2.1p amplitudes. Now once you have a compact expression for propagators, you can just analyze the pole of that propagator, which will give the physical mass square, and the residue will give wave function renormalization. Now to define S matrix, one can just follow LSZ prescription. Now these renormalized masses and S matrix elements defined this way are independent of choice of local coordinates within the gluing compatible class. Now the second issue, shift of vacuum. Consider string theory with scalar field phi and assume that effective action has some quartic tree-level potential. And suppose if you do one loop correction and then that generates some mass term. So it's easy to see that the supersymmetric vacuum shift from phi is equal to 0 to something else which is very near to the original vacuum. And situations like this happen in string theory. If you consider compactifications of SO32 heterotic string theory on Calabi threefolds, one loop correction generate FID terms. Then how will you define amplitudes in the new vacuum? So if you can do some field theory analysis, and that tells that the amplitudes in the new vacuum, which is Fn lambda, that can be expressed as some series of amplitudes in the original vacuum. Here lambda is the vacuum expectation value of the field phi in the new vacuum. Now how will you determine the vacuum? To determine the vacuum, you demand that in the correct vacuum there is no phi tadpoles. That means this F1 lambda should vanish, and that will give an equation for lambda. This you can perturbatively solve, and you can figure out where is lambda order by order. But the problem is that if you look into the right hand side of this expression, the amplitudes that you define in the original vacuum, they contain tadpoles. So they have these tadpole divergences. You need to regulate these divergences by putting an upper cutoff on the S integral for string propagator, where phi state propagates. And you can show that the cutoff tends to infinity limit, all physical quantities are finite, and also there is no local coordinate dependence on these physical quantities. So the upshot is that one can do offshell continuation of Polyakov formulation, and that is unambiguous, and that's useful in resolving issues like mass renormalization and dynamical shift in vacuum, even if you don't have a full-fledged string field theory. Thank you.
All right, well, I'd like to thank the organizers for giving me the chance to talking to all of you. What I will talk to you about is this calculation I did with Joanna Karczmarek at UBC, where we calculated entanglement entropy for a scalar field on the fuzzy or non-commutative sphere. So the idea was to do a simple field theory calculation to try to compare to some recent holography results that have been published. So this is the definition of entanglement entropy that I'm sure a lot of you are familiar with. I'd just like to point out a few things. So first of all, if the system we're looking at is just a set of quantum harmonic oscillators that are coupled, then it's straightforward to actually calculate this without needing holography or replica tricks or anything. And that's just because we know what the ground state is exactly. So it's just a numerical, the only difficulty is numerical. And now if your system instead is a local field theory, and you take, for example, A to be some region of space with a boundary dA, then this diverges. But if you impose some UV regulator epsilon, then the leading order result goes as the size of the boundary dA in units of epsilon. And this result, which we call an area law, is important. It's important to point out that it's dependent on the theory being local. So, in other words, if you think of the theory, the regularized theory, as just a bunch of oscillators separated by some distance epsilon, then the interaction should be nearest neighbor in epsilon. So let me introduce non-commutative geometry and a particular example of non-commutative geometry, which is called the fuzzy sphere. So the idea is just you take your regular coordinates, in this case Cartesian coordinates, and you replace them by matrices that don't commute. For the fuzzy sphere, you take the SU2 commutation relation, so you take n-dimensional SU2 generators, and the reason you do that is that then when you look at the sum of the square of the coordinates, you get that that's proportional to the identity, which morally speaking is what a sphere should be. Of course, this can be made more rigorous, but not in 6 minutes. So among the things you have to do when you go from this commutative geometry to non-commutative geometry is you have to replace your fields by your fields and really any functions by some n-dimensional matrix. And you have to do a few things to your derivatives and to your integrals. And for a free field, this is the Hamiltonian you would get. I should also mention, so because the matrices don't commute, then you can just use the logic you usually use for the Heisenberg uncertainty principle to say that that there's some minimal area that you can probe, and so you can get some inherent non-locality associated with this minimal area. So back to our Hamiltonian, since it's a free field, of course, it stays quadratic. There's nothing special that happens there. And so it's quadratic in every entry of the matrix phi. So we can calculate the entanglement entropy very easily numerically. The only question that remains is how do we associate a particular region to a set of matrix elements? So how do we make this interesting, really? How does this mean anything? Well, we found that if you look at some triangle that basically goes all the way to the top left of the matrix and ends at some point here, then you can associate this region with the function of the field, the value of the field on some polar cap on your sphere. So you can basically, you know, these are integer spaced, so you have a set of thetas that you can match to some degrees of freedom in your matrix. And since we know how to calculate the entanglement entropy for these degrees of freedom, we can calculate the entanglement entropy for this polar cap region with the complement, and we can get some result. So here's the result that you get. This is as a function of the polar angle, and I just turned this into the length of the boundary to make it easier to see what's happening. And of course, the y-axis is your entanglement entropy. So you can see that there's a pretty blatant violation of the area law. It's actually, you know, you would expect it to be a straight line, and it's close to quadratic here. So it's, for small angles at least, it's closer to a volume law than an area law. And I should just mention that, so this gives us some example of, a simple example of violation of area law. There's a few things we still don't understand with this, in particular how the entanglement entropy scales as we scale the size of the matrix. That's a question for another day, I guess.
Okay. Today, I will talk about anomaly polynomial of E-string theories. This talk is based on this paper. First of all, I will talk about what are E-string theories. E-string theories are one class of six-dimensional 1,0 superconformal field theory. So the most famous six-dimensional superconformal field theory is 2,0 series. 2,0 series have 16 supercharges and realized on the coincident M5 branes. But E-string theories are less supersymmetric than 2,0 series, and they have 8 supercharges. E-string theories are world volume theories of M5 branes embedded within the M9 brane. This figure shows the M-theory construction of E-string theories. This is a M9 brane. M9 brane is a 10-dimensional fixed plane of orbifold action on the M-theory circle. On M9 brane, there exists a E8 vector multiplet. And put coincident M5 branes on an M9 brane, we get E-string theories. E-string theories contain the stringy degrees of freedom with E8 flavor symmetry. This E8 flavor symmetry comes from E8 vector multiplet on a M9 brane. As in 2,0 theories, the Lagrangians of E-string theories are not known, and their properties are still mysterious. So I'd like to explain what we have done. For E-string theories, we calculated their anomalies. Anomalies means here gravitational anomalies and 't Hooft anomalies for global symmetry and various mixed anomalies of them. In fact, anomalies are calculable from the bulk 11-dimensional supergravity theory. In order to calculate anomalies, we need not to know about the details of 6-dimensional Lagrangian of E-string theories. This figure shows how to calculate anomalies. On M5 branes, there lives E-string theories. And anomalies of E-string theories means, in some sense, the charge non-conservation, and I represent the anomalies of E-string theories by these red arrows on the figure. Just like current. And we believe that M theory does not contain any anomalies, so we have to cancel these anomalies from the bulk contribution. So the bulk contribution comes from Chern-Simons term in the bulk 11-dimensional supergravity theory. So all we have to know is Chern-Simons term and Bianchi identity for gauge field on 11-dimensional Sugra. So we need not to know the detail of E-string theories Lagrangian. The result is like this. This P2n and I8 and Chi4n and I4 is some topological quantity which characterize the configuration of M5 branes and M9 brane. And these first two terms are due to QM5 branes. Q is the number of M5 branes. And these two terms are like the anomalies of 2,0 theories. And this term cubic in the number of M5 branes is due to tensor multiplet on the M5 branes. And the last two terms comes from the presence of M9 brane, and these two terms is new to E-string theories. So the future direction of this research is to calculate anomalies of other 6-dimensional 1,0 superconformal field theories. For example, put coincident M5 brane on ADE singularity. We get another 6-dimensional 1,0 superconformal field theory, and we can calculate the anomalies of them. And maybe these anomalies have applications to 4D compactification. By compactifying 6-dimensional 1, 0 theory on generic Riemann surface, we get 4-dimensional n equal 1 superconformal field theories. And we can calculate from these anomaly polynomials, from these anomaly polynomials, A and C conformal anomalies of 4-dimensional superconformal field theory. I would like to search these points later. That's all. Thank you.
Thanks very much. Can you just give a hint about how you determine the part of the anomaly that depends on the M9 brane?
M9 brane?
You had the last two terms, chi4, I4,
Yeah.
and I4 squared. Just tell us one or two sentences about how you find those terms.
Yeah, I4 terms comes from the modification of Bianchi identity by M9 brane. So what do I have to what do I have to explain? What?
Okay, thank you. So if my schedule is correct, we have one more talk, which will be by Grigory Sizov on exact slope and interpolating functions in ABGM theory.
I would like to thank the organizers for giving me the opportunity to speak here. My work is based on the joint paper with Nikolai Gromov, and I'll be talking about the exact slope and interpolating functions in ABGM theory. One of the most interesting features of ADS CFT correspondence is the emergence of integrability in the planar limit. Integrability can be understood roughly as existence of infinite number of degrees of integrals of motion, which sometimes give us an opportunity to solve the system exactly. So in our case, to find the conformal dimensions of operators exactly at any coupling. There is a long history of integrability methods in ADS CFT, starting from perturbative integrability at weak coupling, then later developing into this powerful technique of Thermodynamic Bethe Ansatz, which would allow you, in principle at least, to calculate the conformal dimension of any operator at finite coupling, though at the cost of a very complicated calculation. And then recently things boiled down to what seems to be like the ultimate simplification of the spectral problem for ADS CFT. I'm talking about the quantum spectral curve, also referred to as PMU system. In one of the previous talks you already heard about quantum spectral curve for super Yang-Mills theory, and I'll be talking about the extension to ABGM case. ABGM, as you know, it's three-dimensional superconformal theory, which is dual to string theory in ADS4 CP3. And we take a planar limit to see the integrability, introducing the 't coupling lambda. The situation with integrability tools is quite similar, but there is an important difference that S matrix here in ABGM is not fixed completely, but up to an unknown function of a coupling h of lambda, which we call the interpolating function. And unfortunately, this function enters all the integrability-based calculations in ABGM, and it's known up to now only in weak and strong coupling expansions. The good news are that based on the calculation we did, we are able to make some solid conjecture on the exact form of this function. We calculate a slope function that is the anomalous dimension of this operator, a chain of scalars, and S derivatives acting on it, where in the limit when S go into 0. So we use the quantum spectral curve method, and we find the following answer. I'm not going to tell how. What is important is the analytical structure of the basic ingredient of the answer with function I. We will be looking very soon at the analytical structure, so let's notice it has the cut going from 0 to infinity from this factor in each variable, and this branch cut from the square root. Already here you see the answer depends on this function h, which is a known function of the coupling. So how can we find? One method obviously would be if we are able to calculate the same quantity using some other method, for example localization, we would compare the two results, find the function h of lambda directly. Unfortunately, we don't have such a calculation, but what we do have is a lot of exact results about Wilson loops in a BGM from matrix models. So though they are different observables. Okay, yeah, they are different observables, but let's look at, for example, how the expectation value of 1/6 BPS Wilson line looks. It has a form of an integral with 4 branch points, 2 come from the numerator, 2 come from denominator. What is important is that those branch points are known as exact functions of coupling. Here comes our main conjecture, that the 4 branch points of this integral, which expectation value of a Wilson line, should be mapped to the 4 branch points of our result. Once we make this assumption, it's trivial. For example, we can consider cross ratio on both sides. We fix the function h of lambda in terms of coupling, and we get this beautiful result. So let me stress again, this conjecture is based on mapping the analytical structure of the integrand for Wilson line expectation value and the slope function. Of course, we checked that the result reproduces both weak and strong coupling expansions, and it's still a conjecture, so we have to prove it by calculating the same quantity, for example, by 2 methods, for example, by integrability and localization. Thank you.
Thanks very much. I see a question.
Yeah, I don't know. We don't actually know how to generalize, I guess, spectral curve to this case. Could you elaborate a bit?
I mean, the UV description, does it explicitly appear in the conjecture somehow? I mean, where is the critical point where you input the data?
Okay, so, well, so we, of course, so we take this expectation value, basically it's analytical structure, yeah, but
okay, this is maybe you should discuss it more separately. Oh, okay.
I just want to know to what order in the weak coupling is it known?
So there are two orders in the weak coupling known before.
Any other extremely brief questions? If not, then we'll thank our last speaker, but we'll also thank all the speakers for their very well prepared and well thought through presentation, and the audience for their participation in the discussion. Thank you.